Hello everyone. Another example, but this one is more related to circular motion, and specifically it's a uniform velocity on a circular track. For this example here, we're saying about for a car traveling with a speed v around a curve of radius r, determine a formula for the angle at which a road should be banked so that no friction is required. So the car will not be slipping up or down on this curved road with an angle. So just a quick uh, diagram. I'll draw things to make you see the difference, the main difference between um, the curved angle and also the inclined surface. In our previous examples where I discussed the forces, where the inclined surface, that's the inclined surface here where I have a mass, and when I do distribute the forces I will have the mg here, that's the parallel to the incline, and we called it the x component of the weight. This one here was the mg cosine, and the mg cosine, or the y component of the weight, was the opposite to the normal force generated by the surface. However, now for the inclined surface, the curved angle, for the curved angle or the banked angle, bank angle, I have, this is the road, there is a slight tilting here, very small one, and it's very small angle. Usually it depends on what's the purpose of the road, and that's our road. So I will have my car here, that's the car. Now the difference, really, I'm not gonna be tilting the x and y axis, so practically this is still my x-axis, and this one here is still my y-axis, not like the inclined surface where I am completely tilting the x and y related to the inclined angle. Now here, if I want to distribute the forces I have on this car, on this curved road, that will be the mg, or the weight of the vehicle. Now, and there is no need to distribute or analyze it into two components like here. Here it was making an angle with the y-axis. Here it's on the y-axis exactly, so the theta equals 0. On the other side, if I look carefully, the normal force is the one making that small angle with theta. So in this case, I will be analyzing the normal force into two components. One will be here, that will be the normal force cosine theta, and on the x component I will have the normal force sine theta. And this force here is the one will be acting as the central force, because this curve or this road, it's part of a circular track, so there will be a centripetal force acting on this car to the direction, or the direction will be to the center of the circle. That's the direction. Here we go. So the x component of the normal force is the one acting as the centripetal force or the central force. So I just want to take an advantage of discussing the curved angle road with a bank angle to compare it to the inclined surface, nothing else. So for this question here, let's go back to our example where the question looking for how to find a formula for this angle. So I will keep the same drawing here for the curved road, and we're gonna apply it like this. So I have an x-axis. Now from Newton, the total forces equal ma. However, here we're talking about circular forces, so the centripetal force or circular motion, it will be m centripetal acceleration. That's a centripetal acceleration. All right. Now, as I mentioned before, the x component of the normal force is the one acting as centripetal force. So here we go. That's Fn sine theta equal m centripetal acceleration. In fact, I can take this one now and replace it with v square over the radius. That's the radius of the curved road and the velocity of the car, which is a uniform, as I mentioned previously. Now, that's the first part, and I'll stop here for a bit. Then I'll go to the y-axis to test what forces on the y-axis. And it's again ma from Newton's law. This here 0, there is no motion on the y-axis, so there is no acceleration. What forces I have on the y-axis? I will have the normal force cosine theta minus mg equal 0. From here, the normal force cosine theta will equal mg. That will be the second equation I need. Now I have equation 1, I have equation 2. They are the one will help me finding the formula for the banked angle. All right, so I will just take everything out and rewrite things. So the equations I have is the equations I have is F, the normal force, sine theta equal m v square over r, and also we have normal force cosine theta equal mg. That was 1. Here is 2. Now, how we deal with this? Simply, if we divide them on each other, it's going to be like this. Fn r over mg. Now, let's eliminate the normal forces, the masses. So the mass of the vehicle, it doesn't matter in this scenario. From here, sine over cosine for the same angle is tan theta. Then we'll have v square over g multiplied by r. This is the formula, can help me determine many things related to our example when I have a curved road with a certain angle or the banking angle. I can determine how much is that angle. It can help me to know what's the velocity. It could help me find the radius of that curved or that circular track. It depends on what's known and what's unknown in the question. I hope you find this example useful to distinguish between the inclined surface and the banking angle or the curved angle road, and how we process the scenario by distributing the forces. You have to be careful how you deal with the free body diagram in a case like this example of circular motion. I'll see you in the next video where we apply this formula in questions related to circular motion. Thank you.